In the last video, we talked about the different definitions of acids and bases as well as conjugate acid-base pairing. And in this video, I want to talk about relative acid and base strength. So, strong acids are acids that will donate a hydrogen ion 100% of the time when they're placed in solution, and we represent it with a one-way arrow. And that's because for every 100 molecules of the acid you put in, you're going to get 100 hydronium ions. So we draw it as a one-way arrow. When we're talking about a weak acid, that's not necessarily the case. We represent it with a double arrow, which means that it's an equilibrium system. Now, just quickly, an equilibrium system is one where both the forward and reverse processes are happening at the same rate. That does not necessarily mean there's the same amount of reactant as product at any point in time. So a weak acid usually will only result in the formation of product a small percentage of the time, all right? But what determines what percentage of the time that is? The greater the percentage of the time it breaks apart into these pieces, the stronger the acid is, and the less of a percentage of the time that it makes this product, the weaker the acid is. So what determines that is actually the relative strength, basic strength of the conjugate base of the acid. So what that means is, let's just quickly look at this chart. Perchloric acid is one of the strong acids you need to memorize. So this one will give away its hydrogen 100% of the time and result in the formation of its conjugate base 100% of the time. Now this perchlorate anion it's very, very weak as a base, meaning it doesn't grab onto hydrogens really at all. So it's very comfortable just floating around as a soluble ion in solution, complementing the charge of the hydronium ion that's generated in the water as this gives away a hydrogen to it. So the weaker the conjugate base is, the stronger the acid is. And we can quantify this with something called Ka. And this is acid strength. And we'll get into this a bit more later, but I just want to briefly overview it. It's basic. Whenever we're talking about an equilibrium system, we're going to use the symbol K to represent how much product is being made relative to the amount of reactant. So it describes at equilibrium what the ratio of products and reactants really are. Now for an acid, since this is the generic formula for an acid, H, and then the anion that goes along with it, the products are H plus and your conjugate base. So these brackets represent molarity, just as a reminder. The product of these concentrations over the concentration of the unionized form will say how strong it is. So the bigger the Ka, the stronger the acid is, because the greater percentage of the time you have these ionized pieces relative to the unionized form. So again, the bigger the Ka, the stronger the acid. The smaller the Ka is, that means it's a greater percentage of the time that the acid will remain in its unionized form. So strong acids, big Ka, weak acids, low Ka. And we'll get into this a bit more later. Now, there is a list of strong acids you need to memorize and strong bases you need to memorize. So the strong acids that you have to know include hydrochloric acid, hydrobromic acid, hydroiodic acid. Notice these are also all hydrogen halides or hydrohalides, but it doesn't include fluorine. And if you think about it, fluorine is just a really, really small atom, so it really sticks very strongly to that hydrogen relative to the other hydrogen halides. The other ones you have to know are nitric acid, perchloric acid, and sulfuric acid. And weak acids are listed down here, but there are literally millions of weak acids in the world. There are only so many strong. So just memorize the strong and everything else is considered weak. When we're talking about strong bases, again, we don't use Ka to represent the strength of bases. We're going to use Kb, but we'll get to that more later, hopefully. But essentially, alkali and alkaline earth metal hydroxides, because they're very soluble, as you remember from the solubility rules, alkali metals pretty much dissolve with anything, these are all going to be strong bases. So all the alkali metal hydroxides, and then most of the alkaline earth metal hydroxides. And for a similar reason to the fact that hydrofluoric acid is a weak acid, magnesium hydroxide is still a weak base because it's a smaller ion and it's going to have a greater Coulombic attraction to the hydroxides, thus it won't produce as many ions in solution. And we actually have a video we're going to show on that at a later time. But so strong bases, alkali and alkaline